Today we're solving LeetCode 3047, a geometry problem that looks complex at first glance, but breaks down into a clean intersection plus min-dimension pattern. This problem is great for interviews because it tests 2D reasoning, brute force trade-offs, and your ability to simplify geometry into math. You're given n axis-aligned rectangles on a 2D plane. Each rectangle is defined by a bottom left corner, a top right corner. Your task is to find the largest possible square that can fit inside the intersection of at least two rectangles. If no two rectangles overlap, return 0. If two rectangles intersect, their intersection is also a rectangle. The largest square that fits inside that intersection has side length. Min of intersection underscore width, comma intersection underscore height. So the entire problem reduces to, for every pair of rectangles, compute their intersection and track the largest possible square. Let's walk through example 1. Bottom left equals double bracket 1, 1, bracket 2, 2, bracket 3, 1. Top right equals double bracket 3, 3, bracket 4, 4, bracket 6, 6. Step by step. Take rectangle 0 and 1. To find the intersection, we first compute the bottom left corner. The x-coordinate is the maximum of 1 and 2, which is 2, and the y-coordinate is also the maximum of 1 and 2, which is 2. Next, we compute the top right corner of the intersection. The x-coordinate is the minimum of 3 and 4, which is 3, and the y-coordinate is the minimum of 3 and 4, which is also 3. This gives an intersection with a width of 1 and a height of 1. The largest square that can fit inside this intersection has a side length of 1, so its area is 1. After checking all other pairs, no larger square is found, so the final answer is 1. This is a pairwise intersection problem. For every pair of rectangles, we compute the overlap width and height. If both values are positive, then the rectangles intersect. The largest square that can fit inside the intersection has a side length equal to the minimum of the width and height. There's no sliding window and no dynamic programming involved. It's simply a geometric approach combined with brute force and some pruning. Let's try a brute force approach. We try all pairs of rectangles, which gives a time complexity of O of n squared. For each pair, computing the intersection takes constant time. This approach works because the constraint on n is at most 1000. That means n squared is 1 million rectangle pairs, which is well within acceptable limits. Since the brute force solution already runs fast enough, there's no need for a more complex or faster asymptotic algorithm here. This is one of those problems where brute force is optimal. The algorithm works as follows. We loop through all pairs of rectangles, labeled I and j. For each pair, we compute the overlap in the x direction by taking the minimum of their right x-coordinates and subtracting the maximum of their left x-coordinates. We do the same in the y direction, using the top and bottom y-coordinates. If both overlap values are positive, the rectangles intersect. In that case, the largest square that can fit inside the intersection has a side length equal to the smaller of the two overlaps. We compute the area of that square and update the maximum area seen so far. We define a class called solution with a method largest square area, which takes two lists, bottom left and top right, representing rectangles. First, we get the number of rectangles and initialize max underscore area to 0. Then, we loop through all pairs of rectangles. For each pair, we compute the intersection by calculating the overlap along the x-axis and the y-axis. The x-overlap is the smaller of the two rectangles' right edges minus the larger of their left edges. The y-overlap is computed similarly, using the top and bottom edges. If both overlaps are positive, the rectangles intersect. The largest square that fits inside this intersection has a side equal to the smaller of the two overlaps. We then update max underscore area if this square is larger than the current maximum. After checking all pairs, the function returns the maximum area found. Time and space complexity. Time, O of n superscript 2. Space, O of 1. Only constant extra space is used. A few things to watch out for when computing the largest square inside overlapping rectangles. First, always check that both the x-overlap and y-overlap are greater than 0. Rectangles that only touch at the edges don't actually intersect. Second, When computing the largest square, don't confuse area with side length. The side of the square is the minimum of the width and height of the intersection. Third, many explanations assume exactly two rectangles. While more rectangles can overlap, checking all pairs still captures the largest possible square. Finally, make sure to return the area if the problem asks for area, not just the side length. We can reduce the geometry problem to simple math. First, compute the intersection of two rectangles. That gives another rectangle. The largest square that fits inside it has a side equal to the smaller of its width and height. A brute force approach, checking all pairs, is perfectly fine.